Let's start with Siqing Zhang, who's going to talk to us a little bit about non-Abelian Hodge theory and positive characteristic. Thank you.
Thank you. Thank you for coming to my talk. So let me start with X. It's a smooth projective variety. Say over the complex numbers. And then let me just start with Hodge theory. So Hodge in the 1930s defines that every class in the Durand cohomology can be uniquely represented by a harmonic form. As in Durand can be represented by a harmonic form. So that is a form alpha such that we can define a Laplacian on it, and the Laplacian is 0. And it leads to the so-called Hodge decomposition. So if we take the Durand cohomology of the variety, say I look at the degree k piece is given by I plus j equals to k hi x omega x j. So the cohomology of those j forms, and today I just want to look at the k equals to 1 piece. So this is h1 Durand x equals to h1x over x plus h0 of x omega x1. Okay, and so this is the first Durand cohomology. This is the first Tobol cohomology. And then, so earlier, so we have the Durand theorem tells us that the Durand cohomology is the same as the Betti cohomology. And the Betti cohomology in this case is just a hum from the pi1x to the additive group of the complex numbers. And in view of a non-abelian generalization of this Hodge decomposition, so the idea is to replace the C here with any group. So for any group, you can think about pi1 x, and then you just take like this space. You can think of this as a generalized Betti cohomology. Okay, so the natural question is to find the generalization on those two sides. And the idea, I mean, the insight of Simpson in the 90s is that, well, yeah, you can do that. So here we can consider the so-called Durand moduli space with coefficient the additive group. And here you can consider the so-called Tobol moduli space with coefficient. And then you have natural generalization where you can talk about the Durand moduli and the so-called Tobol moduli. And the non-abelian Hodge theorem are about the study of those three moduli problems. So I want to talk about the special case where I just take P just equals to C star, the multiplicative group, and look at what happens. So in this case, if I take C star, I just get C star and say X is a curve with genus P. Okay, so in this case, I just get C star to the 2G. Okay. And so I haven't told you what this Dogol moduli is, but as it turns out, it is going to be S1 2G times R 2G. Diffeomorphic to it. Yeah. And the RAM moduli space is going to be something like this. So this is a trivial R2G bundle over S1 2G, and the RAM moduli will be a non-trivial bundle over S1 2G. So S1 2G and some Fi bundle over it with fiber R2G. Okay. And so this is the moduli space or stack. So this is the moduli of flat G connections, G principal bundles with a connection, and these are the G principal bundles with a so-called Higgs field. So they are moduli of bundles with infinitesimal automorphism. You can think of them this way. Yeah, let me write it down. So moduli bundles with some specific type of infinitesimal automorphism. And so from this example, we see that there are diffeomorph. Okay, so in general, there are so this is also called the Betti moduli space, or let me just write it again. So in general, for general groups, we still get diffeomorphism, but I mean you need to say the words correctly. So over C, we're talking about the semi-stable moduli space of these bundles. So those are moduli space, and over C, I mean the semi-stable condition here is redundant. But let me write it down. So for diffeomorphic for reductive group. And this theorem is a further force of 80s and 90s gauge theory. So it's by the work of a lot of people, teaching Donaldson, Cordet, Simpson, and also a lot of more fundamental works leads to this diffeomorphism. Okay, so this is Abelian Hodge theory in characteristic theorem. And now I want to tell you that so in 1987, Abelian and Illuzi have a purely algebraic proof of a similar result. So they use a characteristic P proof so the Hodge the isomorphism here is canonical for Hodge decomposition, but so they use the characteristic P method to find some non-canonical Hodge decomposition. And I mean that's one of their results. So they use this. So now our variety is over a field of characteristic P. We take the equation defining the variety and then we mod P. And then we basically consider all the lifts from mod P to mod P squared. Consider lift P to mod P squared. And they're like, they give proof for Hodge-Decomp theorem over C. Okay. And then in 20 years later, so Ogles-Rogowski also used those lifts to mod P squared to have a result over characteristics. So now let's say X is in characteristic P, and then we can think about the OX, G, and the RAM XG. So their result is if you put some nilpotent condition, you get an equivalence of categories. So the nilpotent, like so the nilpotent equation for a fixed G, it's like saying that the infinitesimal automorphisms are nilpotent. And their equivalences are also not canonical, but the equivalences are parameterized by those lifts to mod P squared. And their equivalences are also compatible with semi-stability. Now in characteristic P version, the semi-stability in the Durham side is not redundant anymore. So I mean, in characteristic P, you can have connections with P or multiples of P. So in view of this nilpotency, I mean here you don't really see the nilpotency, right? Like here, this factor takes care of the infinitesimal automorphisms, and the nilpotency is like throwing away that factor. So the question is, can we like remove nilpotency? The answer is yes, if we are in a curve case. And in general, the answer is probably no, but I'm not sure. But in curve case, yes, at least for P like larger enough for G. And these are due to also a lot of people like Bedouin, Tapney, Riverman, Gropnik, Cao Chen and Xinwen Zhu. Yeah. And so where's my work? My work is on the semi-stability. So the Ogles-Rogowski, their correspondence holds without semi-stability condition, and they show it without semi-stability condition. So like the starting point of my work is that I show it with semi-stability condition, so you can descend the categorical level equivalences to as certain twisted isomorphisms of schemes. And then from there, you can deduce some cohomological consequences. So why are the cohomological consequences interesting? Is because the cohomology of those three Malin spaces are well studied they are related to the so-called P equals to W conjecture, which says that this is diffeomorphic, so their cohomologies are the same. And here there's there's an interesting filtration on the cohomology called the W filtration. There is an interesting filtration called the P filtration. And the P equals W phenomena saying that under the homomorphism, the two filtrations match. So yeah, there are all sorts of problems, and my work also has some consequences on that. And also, I have a logarithmic picture. Like what happens if we add a simple pole at some points. And it turns out that, so over the complex numbers, there's no, if you want to talk about the logarithmic picture, you have to add some filtrations at the poles. But here we don't need to. And it's gonna be like the M double is like some copies. Sorry, M ram is like some copy of M double without filtration. Okay, that's my part.
Thank you much. Questions?
When you speak of logarithmic, is it for curves or
For curves, yes.
What is the meaning of removing nilpotency? Like, what's the precise statement?
So I can talk about all the Higgs bundles and all the flat connections. So no, so August Rogowski, like in the curve case, like they only deal with the
But then you get this
Higgs
kind of,
fiber.
you're referring to this twisted isomorphism over the.
Right, yeah. They only deal with the fiber over the origin of the Higgs.
So in the original Hodge theory, you have the group be the additive group.
Yes.
So the non-abelian Hodge theory is not really
Right.
a generalization
Right.
of the original Hodge.
It's like it should be called reductive Hodge theory.
Okay. Is there unipotent Hodge theory?
I don't so I think Simpson in the 90s has a paper on some higher things like when you but yeah, let me not say it. Yeah. Sorry. Yeah.
What's the motivation for wanting to replace C with the reductive group? What does that buy you?
I think the original motivation is just that the monoline space are well behaved. Like originally when you construct those monoline spaces, you do some GIP. And for non-reductive group, we like at least I am not so familiar with non-reductive GIP. I mean that's one reason. There are
Over C, you have this kind of hyperplane theorem that can reduce dimension. Do you have something like that here?
Yeah, I'm not familiar with those work. So in Langer's work, I think he has something like in his proof of some Bogomolov-Mialka type inequality, he needs to do some hyperplane, but I'm not totally sure.
Wonderful. Well, let's thank our speaker again.